Hello everyone, myself Dr. Santome Gundu. I welcome you all to this lecture of soft computing technique. This is the second lecture of module 7. So, in the first lecture of module 7, we have studied the introduction of multi-objective optimization. There are many methods to solve multi-objective optimization problems. Some of the methods are weighted sum method, Epsilon-Constraint method, weighted distance metric method, lexicographic ordering method, method of global criterion, reference point method, chips methods, GDF method, and by using genetic algorithm. So our focus will be to solve multi-object optimization problems by using genetic algorithm. Though we will study some of these methods. So first method is that weighted sum method. The weighted sum method is a common approach to solving multi-objective optimization problems. It converts a multi-objective optimization problem into a single objective optimization problem by assigning weights to each of the objectives and combining them into one objective function. So weighted sum method scalarizes a set of objectives into a single objective by adding each objective pre-multiplied by a user supplied weight. Suppose our problem is that to minimize f1x, f2x and so on up to fmx. So now we minimize fx equal to summation I equal to 1 to m wi fi x, where the w are the weights and sum of these weights are 1. So you can say w1 plus w2 up to wm, this equal to 1. Subject g j x greater than equal to 0 for j equal to 1 to l and so on. hkx equal to 0 for k equal to 1 to l and so on. And axi is lies belongs to xi lower bound to xi upper bound. Weight of an objective is chosen in proportion to the relative importance of the objective. So general form of multi-objective problems. So that is there are more than one objective. So consider a multi-objective optimization problem with two objectives, f1x and f2x. f1x and f2x and decision variable x. The problem is typically presented as minimize f1x, minimize f2x, subject x belongs to some region, where x is the feasible region, that is the set of all possible solutions that satisfy the constraints. Steps in the weighted sum method. First one is that assign weights to each objective. Each objective fix is assigned a weight wi that reflects its relative importance in the overall optimization problem. These weights are typically non-negative and sum to 1. That is, sum of all these weights are 1. Two is that format the weighted sum objective functions. The weighted sum of the objectives is created by combining the individual objectives using the weights. The new objective function becomes fx equal to w1 f1x plus w2 fx plus wn fnx. So summation I equal to 1 to n wi fix. So optimize the new objective function to solve the optimization problem as it were a single objective optimization problem. This can be done using standard optimization techniques. So please try to understand one numerical example. Consider the following multi-objective optimization problem. Minimize f1x equal to x square, minimize f2x equal to x minus 2 whole square, subject to x belongs to 0 to 3. We want to minimize both objectives simultaneously. So try to understand, if we say that we want to minimize f1x, so at x equal to 0 we will get 0, and if on that x, that is at x equal to 0, we will get f2x equal to 4. But that is not the objective of multi-objective optimization. So here we want to minimize both objectives simultaneously. So there are the steps by applying the weighted sum method. So first step, assign weights. So we'll assign weights to the two objectives. So that is depends on the importance of the objective. So we are thinking that f1x is more Our aim is to minimize f1x, so f1x importance is slightly more than f2x, so we set weight equal to w1 0.6. If both objects are equally important, then we may say w1 equal to 0.5, w2 equal to 0.5. Here we are saying that w1 equal to 0.6, as we are assuming f1x is more relatively important than f2. So here w1 0.6 for f1x, w2 0.4 for f2x. You can see that sum of these are w1 plus w2 is 1. Step 2. Formulate the weighted sum objectives. The weighted sum objective function will be now f1x equal to 0.6 into f1x plus 0.4 into f2x. So that is 0.6 into x square plus 0.4 into x minus 2 whole square. Step 3 is that we minimize this fx with respect to the x where x belongs to 0 to 3. The objective function is fx equal to 0.6 x square plus 0.4 into x minus 2 whole square. If we expand it, we will get it 0.6 x square plus 0.4 into x square minus 4x plus 4. That is 0.6 x square plus 0.4 x square minus 1.6x plus 1.6. So that is x square minus 1.6 plus 1.6. So now our aim is to minimize this quadratic function. We have to do derivative. So we need to take the derivative with respect to x and we set it equal to 0. We have f dash x equal to 2x minus 1.6 equal to 0 or x equal to 0.8, and you can check f double dash x equal to 2 greater than 0 means at x equal to 0.8 fx has minimum value. Now we need to verify. So verify that x 0.8 is within the feasible region or not. As x 0.8 belongs to the interval 0 to 3, so it is within the range of the feasible solutions. Step 5. Evaluate the objective at x equal to 0.8. So f1 0.8 is x square, so that is 0.8 whole square is 0.64. f2 0.8 is 0.8 minus 2 whole square, so that is minus 1.2 whole square, that will get 1.44. And f 0.8 can be written as 0.6 into 0.64 plus 0.4 into 1.44, that is 0.96. So that's the optimal point x equal to 0.8 result within the following values for the objective f1x equal to 0.64 and f2x equal to 1.44. So conclusion, the weighted sum method has given us an optimal solution at x equal to 0.8. This method provides a way to trade off between the two objectives based on the weight chosen. So I hope you have understood the weight sum method. So now try to solve this question. Minimize f1x equal to x minus 2 whole square. Minimize f2x equal to x square minus 3. Constant is that x belongs to 0 to 10. So you may consider w1 equal to 0.7, w2 equal to 0.3. So construct a function fx equal to 0.7 into x minus 2 whole square plus 0.3 into x square minus 3. So try to solve these questions. Okay. So now solve these questions. So the advantage of the weighted sum method is that it is very simple and it is easy to calculate. Disadvantage, it is difficult to set the weight vectors to obtain a Pareto optimal solution in the desired range in the objective space. It cannot find certain Pareto optimal solutions in the case of non-convex objective space. We will discuss the non-convex objective space, etc. Now, second method is that Epsilon-Constraint method. It is given by the mathematician Helms et al. At 1971. It is keep just one objective and restricting the rest of the objective within user-specific values. So there are so many objectives. So we minimize one object, that is f nu x, subject to f mx is less than equal to epsilon less than equal to the epsilon m, where m equal to 1 to l m, and m is not equal to that mu. G j x is greater than equal to 0, h k x is equal to 0, and xi lies belongs to xi lower to xi upper. So Epsilon-Constraint method is that if f as an objective and minimize f2x and treat f1x as constant, that is f1x less than equal to some constant that is epsilon1. So now try to understand one example of Epsilon-Constraint method. Here we have two objective functions: minimize f1x equal to x square, minimize f2x equal to x minus 2 whole square. Constant is that x belongs to 0 to 4. Step 1, choose the objective to optimize. So consider f1x equal to x square as the objective to minimize. Okay. Step 2 is that convert the second objective f2x, that is equal to x minus 2 whole square, into a constant. So consider f2x is less than equal to epsilon 2. So now we need to solve this. So solve for different values of epsilon 2. So we can assume the number of values of epsilon 2. So for epsilon equal to 0.5. So here we need to minimize f1x equal to x square subject to f2x is less than equal to epsilon 2. So here we assume epsilon 2 equal to 0.5. So x minus 2 whole square is less than 0.5. From here you can write that mod of x minus 2 is less than equal to root over of 0.5. So you can write here that x belongs to 2 minus 0.5 to 2 plus root 0.5. So that is here root 0.5. This is here 2 plus root 0.5. So here x belongs to 1.293 to 2.707. So the optimization problem is now becoming that optimization problem now is converted to minimize f1x equal to x square subject to x belongs to 1.293 to 2.707. The optimal solution is at x equal to 1.293 because this is a simple f1x equal to x square, so at lowest point we will get the minimum. So here f1x, the minimum value is f of 1.293, so that is 1.293 whole square, that is 1.612. So that is first set for epsilon 2 equal to 0.5. Next we assume that epsilon 2 equal to 1.0. So here that f2x is less than equal to epsilon 2. f2x means x minus 2 whole square is less than equal to 1. So x is lies belongs to 2 minus 1 to 2 plus 1, that is 1 and 3. So now the optimization problem becomes minimize f1x equal to x square subject to x belongs to 1 and 3. So here at f1x equal to x square, so your optimal solution will be at f1, that is 1. Now next is that assume epsilon 2 equal to 2. So here again f2x is less than equal to epsilon 2. So that is x minus 2 whole square is less than equal to 2, less than equal to 2. So x minus 2 is less than equal to root mod of x minus 2 is less than equal to root 2. So x belongs to 2 minus root 2 to 2 plus root 2. So that is x belongs to 0.586 to 3.414. The optimization problem becomes minimize f1x equal to x square subject to x belongs to 0.586 to 3.414. So the optimal solution is at x equal to 0.586. So here f1x equal to, that is f1 0.586 equal to 0.586 whole square. So that is, you'll get 0.343. So now need to plot the results. So now we have a few points on the Pareto front, each corresponding to a different epsilon value for constant on f2x. By plotting f1x against f2x, we can observe the trade-off between the two objectives. So then we'll get the final result. So next is that, consider a problem f1x equal to x minus 1 whole square, that is minimize f1x equal to x minus 1 whole square, minimize f2x is equal to x minus 2 whole square. Constant is that x belongs to 0 to 5. So you can assume epsilon, so you can assume in this way that first objective, so minimize f1x x minus 1 whole square subject to f2x is less than epsilon 2, that is x minus 2 whole square is less than epsilon 2. So you can proceed this question. So you can assume epsilon 2 equal to 0.5, you can assume 0.75, you can assume 0.95, you can assume 1.05, you can assume 1.5, you can assume 1.75, and this way you can solve this question. So that is questions 1. It can be for 3 objective also. So question 2 is that, minimize f1x equal to x square minus 5, minimize f2x equal to x minus 1 whole square, minimize f2x equal to x minus 2 whole square, something like that. So here you need to minimize one objective, so you can proceed here, minimize f1x, that is x square minus 5 subject to x minus 1 whole square epsilon 1, x minus 2 whole square epsilon 2. Take need to do the calculations. So here assuming epsilon 1 epsilon 2 as 0.5, you can assume 1, you can assume 2, epsilon 2 you can assume 0.5, you can assume 1.5, you can assume 2. So by assuming this thing, you try to solve these questions. So the epsilon constant method, so the advantage is that, so this epsilon constant method can be applicable to either convex or non-convex problems. So that is convex problem, you know. So this, if the optimal, if the feasible solution space is just like this thing, so you can say this is not convex. If it is just like this, so you can say it is convex. So this is one example. So I'll discuss on these things. So advantage is that it is applicable to either convex or non-convex problems. Disadvantage is that the epsilon vector has to be chosen carefully so that it is within the minimum or maximum value of the individual objective functions. So that is one disadvantage. So in conclusion, so today we have studied two methods. One is that weighted sum method, and second we have studied epsilon constraint method. So question is that, so minimize f1x equal to x square minus 5, minimize f2x equal to x minus 3 whole square, minimize f3x equal to x square minus 4x, constants x belongs to 0 to 10. So solve these questions. Solve this multi-objective optimization problem. Objective optimization problem by using weighted sum method. So you can try for other question also. So that is questions 1. You can change the functions. Questions 2. Formulate any questions and try to solve it by epsilon constraint method. So these are the references of today's class. Thank you.